13 years ago, teams of divers began smashing and clearing millions of purple sea urchins from Southern California's reefs. Nearly 6 million lives erased in the hope of bringing giant kelp forests back from the brink. Decades of overfishing and coastal development had wiped out 80% of the canopy, leaving zombie urchin barrens where more than 700 marine species once thrived. But can engineering an ecosystem by force truly restore what's been lost? Or does it reveal how fragile this underwater world has become? The answer begins with the lost metropolis beneath the waves. Beneath the surface of Southern California's coast, giant kelp, Macrocystis pyrifera, once formed a living metropolis. These underwater forests stretched from Santa Monica Bay to the rocky points of Palos Verdes, their golden fronds rising more than 100 feet from the seafloor. Sunlight filtered through the canopy in shifting patterns, creating a world teeming with life. More than 700 species found shelter and food in the kelp's tangled holdfasts and waving blades. Schools of kelp bass, bright orange Garibaldi, spiny lobsters, abalone, sea otters, and seabirds that dove for fish in the clear water. Kelp forests shaped the rhythms of the coast. They softened the force of winter storms, their dense stands absorbing wave energy and protecting beaches from erosion. Their roots trapped sediment, keeping the water clear and the reefs stable. Every year, tons of kelp drifted ashore, feeding everything from tiny amphipods to scavenging birds. Even the air felt the kelp's influence. These forests pulled carbon from the atmosphere, storing it in their tissues and in the sands below. Generations of people depended on these forests. Indigenous communities, including the Tongva and Chumash, gathered kelp for food, medicine, and tools. Early fishers learned to read the kelp beds as both a map and a larder, harvesting abalone and lobster from the reefs below. For decades, commercial boats collected kelp to make everything from fertilizer to ice cream thickener, while recreational divers slipped through underwater arches and corridors, marveling at the crowds of marine life. The kelp's reach extended far beyond its own fronds. Fish nurseries thrived in the shelter of the canopy, while predators like sea lions and cormorants patrolled the edges. On calm days, the surface shimmered with sunlight and floating blades, a living barrier between land and open sea. During storms, the forest bent but rarely broke, their resilience anchoring the coastline through cycles of change. For much of the 20th century, even as Los Angeles grew and the shoreline changed, these forests endured. They provided food, gyata, and a sense of place for the communities along the coast. Kelp was more than scenery. It was infrastructure, woven into the fabric of daily life. The loss of these forests would mean more than the disappearance of a habitat. It would unravel the connections between people, sea, and shore that had defined Southern California for centuries. By the early 2000s, the underwater forests that once defined Southern California's coast had been reduced to fragments. Off Palos Verdes, more than 80% of the giant kelp canopy was gone. This loss was dramatic and far-reaching. The causes were layered and relentless. Urban runoff and sediment from Los Angeles buried rocky reefs beneath silt, choking out young kelp before it could take hold. Construction and stormwater poured debris into the ocean, clouding the water and smothering any chance for the forest's recovery. At the same time, fishing pressure removed the kelp's natural defenders. Sheephead, spiny lobsters, and sea otters, species that once kept purple sea urchins in check, vanished from much of the coastline. Without these predators, purple urchins multiplied. Their numbers soared to densities of 30 per square meter or more. But this was not a population boom in the usual sense. Starved of kelp, the urchins entered a state scientists call zombie mode, hollowed out, nearly devoid of reproductive tissue, but still able to scrape every last trace of algae from the rock. Even in this weakened condition, they were relentless grazers. Any kelp spore or sprout that landed on barren reef was devoured before it could grow. Marine heat waves and the sudden loss of sunflower sea stars from disease only deepened the crisis. Heat stressed the kelp, making it harder for new fronds to survive. The disappearance of sea stars, themselves key urchin predators, removed another line of defense. With each passing year, the feedback loop tightened. More urchins, less kelp, less habitat for predators, and so on. The reefs became locked in what ecologists call an alternative stable state. Not a healthy forest, but a persistent barren. Here, the system resists recovery, even when fishing stops or water quality improves. The urchins, despite their meager condition, hold the ecosystem hostage. Conservation policy tried to respond. Marine protected areas were established, and fishing regulations were tightened. But these passive approaches assumed that if human disturbance was reduced, nature would rebound on its own. In reality, the barrens barely budged. Inside protected zones, urchin densities remained stubbornly high. Kelp failed to return. The logic of protection alone, without direct action, proved insufficient against the sheer biological inertia of the urchin-dominated reefs. This standoff revealed the limits of traditional management. It was not enough to stop harm. The system had settled into a new equilibrium, one that excluded kelp and the hundreds of species that depended on it. The coastline, once buffered by dense forests, now faced storms and erosion with little natural defense. Fisheries that relied on kelp, from lobster to red urchin, dwindled or collapsed. The loss was not just ecological, but economic and cultural, a silent unraveling that left the ocean less resilient, and local communities with fewer options. Only a direct challenge to the urchin stronghold could open the door to recovery. In 2012, a new idea took hold among restoration scientists and local divers. If the relentless grazing of purple sea urchins was locking reefs in a barren state, then perhaps the path to recovery was not to wait for nature to rebalance, but to set a precise, measurable target for action. The Bay Foundation's project lead argued that the system was stuck, and only a deliberate intervention could break the cycle. Drawing from field experiments and published studies, the team settled on a clear goal: reduce purple urchin densities from the observed average of 30 per square meter down to just 2. This was not about eradicating every urchin, but about dialing back their numbers to a level where kelp spores could survive long enough to take root. The rationale was rooted in data. At densities below 2 urchins per square meter, kelp recruitment surged in test plots. Above that threshold, any new growth was grazed to nothing. The restoration lead described it as treating urchins like a control knob. Turn it down, and the system could flip from barren to forested almost overnight. Setting a target density made the project measurable, repeatable, and, in theory, scalable. It also gave divers a concrete benchmark for their work. Not just clearing urchins at random, but systematically sweeping each restoration polygon until the magic number was reached. This approach demanded careful planning and coordination. Teams mapped out the reefs, divided them into polygons, and tracked urchin counts before and after each sweep. Every diver hour, every hammer blow was logged. The project became a living experiment, guided by the conviction that science and sweat, applied with precision, could restore a lost ecosystem. A veteran diver straps on his tank in the pre-dawn dark, hands already aching from the memory of yesterday's work. The plan is simple in theory. Drop into the surge, find your polygon on the reef, and start swinging. But nothing about this job is easy. The polygons, mapped grids covering more than 80 acres of rocky bottom, are marked and logged with GPS, each one a battleground in a war of attrition. Divers descend in pairs, hammers in hand, scanning the reef for clusters of purple sea urchins, wedged into cracks and crevices. The rules are strict. Don't try to clear every last animal, just bring the count down to 2 per square meter. Any more, and the kelp won't stand a chance. Over 13 years, the numbers pile up like the urchin shells left behind. 15,000 diver hours logged, longer than most people spend at a single job. Nearly 6 million purple urchins smashed or scooped up. The effort is relentless, the pace dictated by tides, visibility, and the ever-present risk of entanglement or exhaustion. Some days, the surge knocks divers against the rocks, scraping knuckles raw. Others, the water is so murky you can't see your own gloves. Every urchin is crushed in place, left to break down on the reef, food for crabs, snails, and whatever scavenger finds it first. The stench of decay is brief, gone with the next tide. For the divers, the satisfaction is in the numbers. Another polygon cleared, another patch of reef ready for kelp to return. A monitoring scientist kneels at the edge of a rocky reef, clipboard in hand, ready to record what the ocean reveals. The restoration team uses a grid of underwater transects, straight lines marked on the seafloor, both inside treated polygons and in untouched barrens nearby. Divers swim along these lines, counting every purple sea urchin within a measured belt, recording the number per square meter. They note not just the urchins, but also the height and density of kelp stalks, the presence of abalone, lobsters, and fish darting through the fronds. Every count is entered into waterproof slates, then transferred to spreadsheets back on shore. To capture the bigger picture, satellite images and drone flights track the spread of kelp canopies from above. Scientists compare data from polygons where urchin densities were reduced to 2 per square meter with those left at original levels, watching for differences in kelp growth and animal returns. In some plots, they sample red urchins for gonad weight, a key indicator of reproductive health and economic value for fisheries. Consistency is everything. The same protocols are used year after year, same transect widths, same timing, same methods for estimating canopy cover and fish biomass. Mistakes and outliers are caught by repeating surveys and cross-checking results between teams. The monitoring scientist describes the process as building a chain of evidence, each link tested and double-checked. Only through this careful, methodical work can the true impact of urchin removal be measured, not just in numbers, but in the living fabric of the reef. Kelp canopies, once nearly erased from the reefs off Palos Verdes, now stretch overhead in thick golden ribbons. Satellite images and diver surveys show a dramatic transformation, where less than 10% of the reef was shaded by kelp before. Restored areas now boast canopy coverage between 50% and 80%. Fish transect data reveal that kelp bass, once scarce in the barrens, have returned in numbers approaching those of reference forests. Invertebrate counts echo the trend. Abalone, lobsters, and red urchins are reclaiming their place among the fronds. The red urchin fishery, devastated by years of barren rock, is showing signs of life. Gonad indices, indicators of inequality, have soared, with some plots recording more than 8 times the biomass seen before restoration. The numbers are checked and rechecked by independent scientists who track the rebound of both canopy and community. One marine ecologist describes swimming through these restored patches as a return to an underwater cathedral, sunlight filtering through columns of kelp, fish weaving in and out of the living architecture. For those who have spent years measuring and mapping these changes, the evidence is clear. Targeted urchin removal did not just open space for kelp, it brought back the pulse of an entire ecosystem. A veteran diver sits on the edge of a small boat, hands scarred from years of work, remembering the first time he was paid not to harvest, but to destroy. For decades, his living came from pulling red urchins, those prized for their rich uni, from reefs thick with kelp. When the barrens took over, the market collapsed, and the old rhythms of fishing life fell apart. The restoration project offered a new kind of work. Don a wetsuit, drop below the waves, and swing a hammer at purple urchins instead of gathering the red. The shift was jarring. Some saw it as a rescue, others as a last resort. He says it is not what he thought he would be doing at 50. But when you come up and see kelp again, you know it is worth it. Local fishers and divers traded stories on docks and in dive shops about the change. Some hesitated, holding out hope that the old fisheries would rebound. Others joined the restoration teams, drawn by the promise of steady pay and a chance to repair what was lost. Volunteer divers, many from the community, signed up for weekend monitoring shifts, logging hours underwater to track the forest's slow return. The project became a patchwork of paid labor and volunteer effort, blending pride, skepticism, and a stubborn hope that the coastline could recover. For many, the work was more than a job. It was a way to reclaim a sense of belonging to the forest beneath the waves. The question of whether it's right or wise to kill millions of native urchins for the sake of a forest has never left the surface. An ethicist who spoke at a public hearing described the project as a moral puzzle. On one hand, the urchins are native, not invaders, and their destruction is deliberate and systematic. On the other, the entire ecosystem, kelp, fish, even the livelihoods of local people, depends on shifting the balance. The ethicist pressed for a reckoning with the precedent being set. If it's justified here, what stops the next intervention, or the one after that? Is this restoration, or are we simply managing symptoms while deeper causes like warming seas and predator loss go unaddressed? A regional manager with the Bay Foundation faces a different kind of limit. The cost of restoring even a single acre runs into the tens of thousands of dollars. The project's budget, stitched together from grants and public funds, can only cover a narrow band of coastline. Scaling up to the full sweep of California's barrens would require sums that no agency has on hand, and a diver workforce that does not exist. The manager is blunt. The project works, but only in patches. Every decision is a trade-off. Where to spend, where to hold back, which reefs are saved and which are left behind. Meanwhile, the practical aftermath of mass culling is less dramatic than some feared. Crushed urchins decompose quickly, feeding crabs and other scavengers. Monitoring teams report no widespread water quality problems or dead zones. The nutrient pulse is brief and local, swept away by currents. Still, the sight of empty shells strewn across the reef is a reminder that restoration at this scale comes with its own cost. Each cleared polygon is both a victory and a question about what it means to take responsibility for a wounded sea and how far society is willing to go to repair it. Today, kelp forests off Palos Verdes are proof that ecosystems can be engineered back from the brink, if the will and resources persist. But with climate extremes accelerating and with much of California's coastline still barren, deliberate intervention is no longer the exception. How we choose to manage nature now will decide which underwater worlds endure and which become memories lost beneath the waves.